question going to take?
25 minutes. What we've been talking about so far, rational functions, we have had, and you can go back to the top of the notes, I believe it says, when we defined a rational function that R of x was equal to P of x over Q of x, where P of x and Q of x have no factors in common. Okay? So everything we've been graphing so far, there were no common factors in the numerator and denominator. Okay? However, that is not uncommon. You can have common factors in the top and the bottom, per whatever your individual polynomials are. Okay? And we're not going to realize those or recognize those until we factor both polynomials completely. What we've been talking about is that your denominator, so far, always provided you where vertical asymptotes were located. Does that make sense? Because of division by zero. And what I want to amend that a little bit. I want to change that. I want to say that your denominator is always going to provide you where you're going to have discontinuity. Okay? You're going to have undefined values because you're going to still have situations where you have asymptotes. In this problem, we're still going to have at least one asymptote. But because you may have common factors, a common factor can be canceled. Okay? And just the behavior that happens to the left and to the right of x values that are close to the x value of that common factor, you do not end up getting asymptote-like behaviors. Okay, so if we were to evaluate, so what's going to happen? Let's look at this. Let's factor this bottom. What's that bottom going to factor to here? Okay. So what happens when I evaluate this thing at like 3.1, and then 3.01, and 3.001, and 3.0001, or at 2.9, and 2.99, 2.999, 2.99999. If I evaluate at those values, we do not see the y values kind of darting off to positive infinity or negative infinity like we do with asymptotes. Okay? And you can kind of, maybe if we take, I don't know, Desmos. And type in this function x minus 3. And actually I'm going to go a minus 3 just so I can use a slider here. A squared minus 3a. And as I choose values that go between, so let's say we want to go to the right of 3. So let's go 3, and I'm just going to make this then like 3.1. Okay. If I do, obviously it's undefined at 3 because that would be division by 0. But if I'm to the right of, so pretty in regards to 3.1 and how close I can get to 3, 3.1 is pretty far away from 3. But if I start moving this thing down, okay, closer and closer to 3, is this number getting closer and closer to negative infinity or positive infinity like it does during an asymptote? It's not, right? Okay. If it was an asymptote, so the idea, if it was an asymptote, so there's going to be an asymptote at 0 for this thing. So let's say that we're going between 0 and like 0.1. There, what is that y value doing? That y value is now increasing much faster, right? Okay. I don't know how close I can get. But you can see that that is darting off to be larger and larger y values, okay? But at the 3 value, it was not doing that because of the evaluation there, and this canceling idea is we actually have, at that value of 3, we have a similar behavior of what the graph of 1 over x would do at 3 instead of that asymptote-like behavior. Does that make sense? Okay. So if we cancel the common factors, that's what we end up with, 1 over x. So what we're going to find out when we graph these things is this graph and that graph are 99.9999999% identical. They are almost 100% identical, except for at one point. Okay? Even though those things cancel, I still cannot plug 3 into the original function. Okay? You cannot plug 3 into this, right? Because you're going to get 0 divided by 0. 0 divided by 0 still contradicts, I don't want to say contradicts, it still abides by the rule that we're not allowed to divide by 0. Okay? So, if we're not allowed to divide by 0, even taking 0 and dividing by 0 is not allowed, we've got an issue at x equals 3. So right now in this problem, when I factor it, we know we have a vertical asymptote at x equals 0, but now we also have a hole at x equals 3. Okay? So that's why I don't want to change the way that we phrase what we do with that denominator. Okay, the denominator is now, instead of just finding asymptotes, it's where we find discontinuities. Okay? I always take the approach that I'm going to look at my denominator, and they're all going to start off as asymptotes. I'm going to find all the zeros of the denominator, and they're going to start off as asymptotes. Once I list those, then I'm going to go back and say, okay, which ones of them are common to the numerator? And then it changes it from an asymptote to a hole. Does that make sense? Okay. Now, holes are going to be in your two-dimensional plane. So they don't just have one coordinate, like x equals 3. They have a y coordinate. Okay? It's somewhere on my graph. So I want to find out what that y coordinate is. Well, if I know what x is, then y is found by just plugging back into the function, right? If I plug back into this function right there, with x being 3, what do I get? What's 3 minus 3? 0. What's 9 minus 9? 0. What's 0 divided by 0? Can't do it, right? So that doesn't give me a y value. But if these two things are identical, except for at that one point, this doesn't have that discontinuity at 3. Does that make sense? If we graph 1 over x like we did 2 days ago, 3 days ago, there was no discontinuity at 3. So if these two graphs are identical, except for this one hole, then I should be able to plug this in there and get y to be 1/3. Does that make sense? So if we were just looking at 1 over x, that was the problem that we start with. There are no holes, and there would be a point 3 comma 1/3, right? It would be shaded in on my graph. If we look at x minus 3 over x squared minus 3x, it is the same exact thing as 1 over x. But except now at that point 3 comma 1/3, instead of it being shaded in, it's an open dot. Because we have a point discontinuity there.
Is x equals 3 not a real graph because it's a hole?
Yes. Yes. So when we graph this, I'm going to do this in GeoGebra just to make it a little bit quicker to make our comparisons. If I look at x minus 3 divided by x squared minus 3x, we get that graph right there. Okay. Now this graph, this gray graph, does not, and no calculator that I've ever come across will do this, it does not visually put the hole on the graph. Does that make sense? Okay. And for the reason that one hole is a very, 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 very small position. So like if they put an open dot here, it would just graphically be a problem. Even if I zoom in on it, like you're not gonna, no matter how far you zoom in, it's not gonna be like a gap here. Okay. So the only way I can recognize that there is a hole there is actually to take my function and say, if I take f and I evaluate it at 3, what does it tell me? It tells me it's undefined. So that's how I know there's a hole there. Does that make sense? Okay. Now if I graphed 1 over x, I get that red function. Is that red function the same as the gray one? Looks the same, right? Okay. But on the red one, if I ask what G of 3 is, you see there it gives me back 1/3. So if I graph that point, 3 comma 1/3, on the red graph, on 1 over x, that point should be shaded in, like we did 2-3 days ago. Okay? But on the gray graph, that point A should be an open dot like that. Okay? And that provides, we call that point discontinuity. If you guys remember, when we talk about things being continuous, yeah, this whole graph lacks continuity because of one of the asymptote and second that hole there, A. But if I were just like look at this branch in the third quadrant, can I trace that entire branch without lifting my finger? So we could say that on a defined interval from like negative infinity up to 0, not including 0, that this graph would be continuous, right? So you can look at, you can kind of make a window with an interval and say, okay, we're continuous in that window. But if I look at this branch in the first quadrant, okay, it is almost 100% continuous. I put my finger up here and I start dragging down towards A. Now, if there's a hole there, to get to the other part of the graph, I don't have to lift my finger off the graph, put it back down on the other side, and then graph, right? Okay. So we have point discontinuity there at A. Okay. Does that make sense, everybody? So division by 0 is always going to provide you some type of discontinuity. You then need to distinguish, is it a vertical asymptote or is it a hole in this case? Okay. So you may have questions on that kind of analysis. You can have multiple holes. You can have 2, 3, 4, 5 of them. It just depends on how many factors you have in the numerator and denominator that are common. Yes. Yep. Yep. And it's because that's a factor of 1, and then around that value, kind of using that evaluation process, that factor of 1 leaves, when we evaluate, terms that are not going to make your graph around that point drastically increase or drastically decrease like it does in an asymptote. We cool with that? Andrew?
Yeah.